I sure can't sleep. Man, I wonder why I couldn't sleep.
Maybe it's because you're not on a sleep train mattress.
Whoa. I probably couldn't sleep because I wasn't sleeping on a sleep train mattress. How do we make one of those? But what could that sleepy goodness be made out of? Polyurethane. Hello, my name is Liam Isaacs, and I'm here to tell you, Sleep Train, why polyurethane is not only the best choice, but how you apply it and how you make it. Polyurethane. You see this? That comfy mattress material is actually made up of this, which its chemical formula is a benzene ring connected by urethane linkages, in which could be represented by R, and then you have the urethane linkage connected to another R, with the head group of CH2 and CH2. So, some facts about polyurethane. One, it's composed of a chain of organic lengths, which means organic means containing carbon, and it's a thermosetting polymer. And what that means is that it's a petrochemical material that irreversibly cures. And what curing is the toughening or hardening of a polymer by cross-linking of polymer chains. So what that would look like, this could be induced by heat additive, a strong chemical additive, suitable irradiation, or as you can see here, an electron beam in which you apply a beam of electrons to this material. And you can see that on the, you pretty much redo what Thomson did in his experiment, except apply that to polyurethane. Now, some patterns among given data. We know that the hardness of polymers in general would be nothing to 7. We have the tensile strength 50 to 152, elasticity 0.05 to 5.5. So this means it's pretty elastic, it's not that hard, and it has a lot of tensile strength, which means it won't break that easily under pressure. Has a pretty high melting point, which you can see here is a diagram of generic melting point, not pertaining to this specific set of data. And you can see that it has a fairly high melting point because that means that its bonds are pretty hard to break. Because when it's melting, it's changing phase state, and what that pretty much is breaking bonds. And so when we, I'll talk more about bond strength later. So in the curing process, we know that that's irreversible, and the conjugated system, we know that's a somewhat conjugated system, and I'll get into that a bit later too. So the weakness of that, just some limitations, is that it lacks units. It's just, that's implicit, but it's not very explicit. It's a broad categorization based on low sample size. So it doesn't discuss potential subset categories of polymers, such as self-siphoning polymers, which actually will pour themselves out of a beaker when positioned somewhat diagonally. And we know that it could be a semi-crystalline structure, which is depicted in this diagram, depending on just the way the polymer is constructed and formatted. And you can see that this is when it cross-links. We don't know the exact diagram of when it's actually performing under pressure. So curing. BTDA, which is a common chemical, cures through addition of polyox, which is a self-siphoning polymer, and heat. So you can see this in the chemical diagram. You have benzene rings, which are very common. Polymers are usually aromatic compounds, with the addition of polyox with heat as a additive without actually adding any chemicals to the reaction. And you can see that the link sort of hardens or toughens, and you can see this on the physical level. It would be less elastic and less bendy. It will have more, will be put under stress and undergo cross-linking. And in this case, it was done through heat. That's not the only way. Heat and chemical additives. That's the main way, but not the only way. So urethane, which is also known as ethyl carbamate, molecular formula of C3H7NO2, is an ester of carbamic acid, which is NH2COOH. It has a very high melting point. And cures generally about 200 degrees Celsius. Chemical additives or suitable irradiation. And these scenarios are how this pertains to our product as a mattress. This is very, it is not common that you see suitable irradiation, electron beams, any of those being applied to a mattress that people are sleeping on. Unless you have a person that is above 200 degrees Celsius, will the mattress actually melt, which I really, really doubt will happen. So if we continue here, the synthesis methods, there's two, and the first of which is it's a white crystalline substance, first of all, urethane, produced by action of ammonia, NH3+, on ethyl carbamate. You can see this in the chemical reaction. The chemicals are balanced, and you end up with ammonium chloride. You can see that there's only chemical additives here. There's no heat like before, and then you end up with double replacement reaction. And that's just the chemical formula of it. If you have the second method of synthesis, which is less common, the first method is the one I've mainly proposed in factories, as it is not only very, very cheap, but also very easy to do. The second method is heating urea nitrate, which is that and ethyl alcohol or ethanol. And this is adding and heat, so this is two actions. And you end up with this and ammonia on its lonesome. So, the application of it, you can use these synthesis methods to produce a synthetic polymer, meaning that it's synthesized from two different monomers, polyurethane, and bond these units together to produce a mattress. And what that would pretty much, what a mattress would look on the chemical level is the cross-linking under stress of polyurethane. And then the conjugated system is the stability. And it could also be dyed, as depicted in this photo. You could create it any color you like, although I really doubt that anybody wants to color their mattress. So the performance under stress, you know that there's very hydrogen bondings that spread out. There's a heat. This occurs on a heat additive, stress application, pressure increase. Pretty much, this is a very common thing among chemicals, and it's not that rare to come across. And you can see that the bonds are a bit more further apart. And then conjugated system. So what this means, what conjugation is pretty much overlap of one p orbital with another across an intervening sigma bond. And what this looks in benzene is that you have the double bonds alternating, which are pretty much just meaning that you have a pi bond, and that they are, in benzene it alternates between sp3 hybridization and sp2 hybridization. And what that would look like on the molecular level is that you have p orbitals that overlap and create two delocalized electron clouds, which are known as, this is a conjugated system, right? So, and if you have polyurethane, which has benzene in it, or is an aromatic compound, you're going to have a somewhat conjugated system due to that fact. It can be cyclic, ring compounds, acyclic, linear, mixed, as in the in reference to the molecular geometry. So, orbital structure of benzene, as I've said before, which is cyclic and aromatic. And principles of color chemistry, pretty much that color chemistry involves absorbing light in the visible spectrum, and it has at least one chromophore. What this pretty much means, an exhibited resonance of electrons, what this pretty much means is that it is possible to apply color to polyurethane. It is a thing that you could do due to the principles of color chemistry. So comparison to polypropylene. So this is why we wouldn't use another material for sleep-clay mattresses. This one is a thermoplastic polymer. And what that means is it becomes pliable and moldable above a specific temperature and solidifies upon cooling. So when we go back to the observed patterns among data, this would rank lower in the melting point, as it has a lower specific heat capacity. So when we look at polypropylene, it looks like this in a chemical formula, and this in terms of the physical representation of what it's commonly used for. And just upon observing this, you can see that there is no way in hell that a mattress company would want to make their mattress out of plastic, but that's the common use of an alternate chemical. You can see that it's also associated through intermolecular forces, which we can, under temperature application, of course, can mean yielding a viscous liquid in some cases. When melting, if you've ever melted plastic or any thermoplastic polymer, it's going to end up with a viscous liquid, and it's an engineering plastic. So, and what this would look like in a chain of it, which is incredibly redundant for me to analyze, however, it would look like this on the molecular level, which is the same thing as what I said before, as the bottom right there. On a structural level, it looks like that. So it's also isotactic, which means it can be arranged in various ways. It's not regulated to one representation, and the substituents located at the same side of the macromolecule backbone. So you could say here's an example of an isotactic molecule which has the molecular backbone the substituents are located at the same side of the molecular backbone. Why polyurethane? As I said before, it's a thermosetting polymer. And just a generic phase diagram here. Of course, it wouldn't undergo sublimation or anything. It wouldn't subliminize, but it would occur in its boiling point or in its melting point. Normal boiling point, critical point wouldn't reach a supercritical fluid. We wouldn't have to worry about that. Wouldn't have to worry about the triple point all that much because it would mainly maintain itself as a solid as its melting point is fairly high, and that in any circumstance which a normal person would have a mattress, they wouldn't undergo such phase change. However, if you use polypropylene, there is a low chance that they would undergo phase change, but the main reason why we turn to polyurethane is its physical appearance and its physical attributes, its properties are much more bendable per se and less sort of plastic-like than polypropylene. So summary of its efficacy: it's able to be colored and endure stress. Its own organic structure consists of urethane, which is ethyl carbamate. Linkages between benzene compounds and can be reduced through efficient means, which is an action on ammonia and ethyl carbamate.